Thank you. My name is Jyrkinen. I'm representing Team Switzerland, and here's my presentation on problem number 6, hurricane balls. So let's first have a look at the task statement. So task statement starts off with a description of the hurricane balls, namely 2 steel balls that are joined together. It continues with a description of the motion, that they can be spun at incredibly high frequency by first doing them by hand and then going on them to a tube, which is the onset of the motion in this task. Finally, you conclude with a very open-ended task statement to simply explain and investigate this phenomenon. So to give you a better idea of what is going on here, here's a quick video demonstration. So as you can see, the hurricane balls, they spin with a certain inclination angle to the horizontal. Now, to some preliminary observations. So different observations can be made if we experiment with these. So firstly, a lift-off can be achieved if we spin these hurricane balls. Secondly, the angle theta, which I have sketched here, it decreases with an increasing spin rate. That means the hurricane balls stand up if we increase the spin rate. Thirdly, they spin with an inclination angle to the horizontal. Fourthly, the same angle which I've sketched in the sketch, it levels off at some maximum value as the spin rate continues to increase. So we can keep increasing the spin rate of this hurricane balls, but this angle won't increase anymore. Fifthly, over a longer period of time, if we look at these hurricane balls, then they slow down and the inclination angle becomes large, so they dip. So the first observation, so why we have a lift-off. If we have a look at this video, then you can see that we first spin them by hand. Now what happens is, if we spin those balls, then we apply a torque, which produces an angular momentum pointing into our direction in this case. So from the side view, we can say that as soon as there's a slight perturbation at the surface, then these hurricane balls, they are forced to stand up. And because of the law of conservation of angular momentum, this new component, which has been produced by the slip-off, has to be compensated by angular momentum, which is pointing into the symmetry axis. Therefore, this would produce a sliding friction force at the contact point, because it's still spinning now about the symmetry axis, and this would produce a torque which would cause the angular momentum vector to rise. Now to the second observation for why we have decreasing angular theta. Now, if we look at this sketch, we have these two angular velocities about the symmetry axis and about the vertical. These produce an angular momentum which is pointing in this direction as seen in the sketch. Now, if we apply an external force, for example, with the drinking straw, then we produce an external torque which would cause the angular momentum vector to rise. Now, this external torque, in our case, was produced by an air pipe. You can see it here, the nozzle with which the hurricane balls were spun on this cup, and with this, we could control, with this air pressure, we could control the terminal angular velocity for these hurricane balls. To the third observation, for why these hurricane balls spin with a certain inclination angle. Now, this can be explained by precession. We have the angular momentum. If we first imagine that these hurricane balls are just spinning about the symmetry axis without any surface, then the angular velocity points in the symmetry axis. This produces angular momentum vector pointing in the same direction. Now, as soon as we place these hurricane balls onto some surface, this will produce a normal force. This normal force itself will produce a torque, and this torque is what's responsible for the change in the direction of angular momentum, which will cause the precessional motion. Now, to understand the next observation, we have to cover some basic theory. So we've already covered that there's a precession due to the normal force, because it produces a torque. Now, this is produced by the normal force, as already explained, and this angular momentum vector is just the moment of inertia tensor times the two angular velocities. Now, it is useful to introduce body fixed axis 1, 2, 3 in this system, because with that we can express the moments of inertia of these hurricane balls in this body fixed system. We can also dissect the angular velocity in the vertical direction into these body fixed axis, and if we do that, we get the following equation for the horizontal part. This can be combined with this equation, and we get this equation. Now, for this equation, it's important that we assume that there's no slip condition, that there's a purely rolling motion. Now, if we have a look at the contact point, which is here, it traces a circle both on both the hurricane balls and on the floor, on the supporting surface. Because we want that there's a no-slip condition, the two velocities we want to be two on the circle have to be equal, and due to geometry reasons, the radii are equal, and this means that the two angular velocities are equal. Now, to the third observation for why there's a limiting angle inclination angle. Now, algebraically, this can be just solved for this angle. If we increase omega to the infinity, we will get this angle. On a more physical level, we can understand this. If we apply some external torque, then this would cause the angular momentum to rise. But as this angular momentum vector isn't aligned with the symmetry axis, it reaches the vertical sooner than the symmetry axis of the hurricane balls. Because at some point, it would just be the angular momentum would be in the vertical, whereas the symmetry axis isn't. Now to the experimental setup. For this explanation, for this following experiments, I already showed this cup setup. And this cup was made sure that it is horizontal, so there's no sort of curvature. I used different sized balls for these experiments. Now we can test this equation I already introduced by just solving for this theta, and we can see there's a good correspondence between data and theory. But everything I've covered so far, this theory I've shown you, is just known theory. It's already known from literature. But as the task then just states that we have to have two steel balls that are joined together, it doesn't specify the distance or the radii of these spheres. And this known theory only works in a very special case where the radii and the masses are equal. But what happens if we vary the distance, the size, or even both? Now, if we try to apply this theory we already have for different distances, we see there's a very bad correspondence. Also for the different sphere size. And for the most general case, there's also very bad correspondence. But now, it's not important to note now, if we try to introduce a model, that this general model, that these three cases are a special case of this, with these conditions. Now, we have to introduce, think about what we have to change for this general model. To do this, we have still the precession due to the normal force, but this normal force, as the levers now are different, has to be adjusted. If we do that, we get this following equation. The angular momentum still is the moment the inertial tensor times the angular frequency, and these two, if we still want to assume that there's no of conditions, but as the two radii traced by this contact point aren't the same anymore, we have to adjust that. And finally, the moments of inertia are different because now the center of mass is shifted and the two spheres aren't the same, so we have to adjust that to get new moments of inertia for our new model. Now, if we make these adjustments, we get this following generalized model for this case. Now, note that if the distance is 0 and the radii are equal, we get the formula, we get the model from the literature. Now, if we try to apply this formula to our theory, to our data points with the different sizes, we see there's a very good correspondence. Also for the different sphere size. And finally, for the most general case. Now, everything we've covered so far only describes the steady-state motion. But this steady-state motion only holds true for very small periods of time. And in these small periods of time, we can say that the angular velocity and the angle can be seen as constant. But as soon as we, as you can see in this video, we can say that they're constant. But as soon as we look at longer time periods, we can't assume that anymore. Because there are energy losses due to the rolling, mainly due to the rolling friction and the air drag. So we can visualize this. Here are different frames taken in about 10-second distance. And as you can see, this inclination angle certainly decreases. Now, to describe this time development of how this angle and this precession frequency decrease, we can describe this mathematically using a Lagrangian. We can once again introduce the body fixed axes 1, 2, and 3. If we do that, we can then express the kinetic energy of this hurricane ball and the potential energy of the center of mass of these hurricane balls. We have to introduce generalized coordinates for the Lagrangian, and if we now look at the contact point of this hurricane ball, then here's an exaggerated path of this hurricane ball on the subcomposite surface. We have to introduce Cartesian coordinates. If we now look at the contact point at the position x, y, this would have the coordinates described in this system as seen here. But now we also have this air drag and rolling friction, which are these dissipated forces in this system. So we can say that this contact point has a certain velocity in this direction, and opposite to this direction, we would have this dissipated force F, which would be the rolling, which would be the air drag and the rolling friction. Here, the V is just a unit vector to give the direction. Now, to the generalized forces, we can then describe this dissipated force as generalized forces for the Lagrangian. And if we do that, we can solve these with the Euler-Lagrange equations and our dissipated forces. And if we do that, we can calculate how the inclination angle decreases and also how the corresponding angular velocity decreases. If we do that, we can see it predicts this quite accurately. Now, it might seem in this diagram that this model predicts multiple, predicts multiple angles for a given time point. This is not the case. If we zoom in into one of these sketches, we can see that it just predicts a very large nutation, and it still holds true for this data points. We can now also look at a much smaller time frame, not just in these 10 seconds of time periods where we look at this time points. If we make a measurement for a very brief moment of time, we can see that this nutation is predicted quite accurately. Now, for clarifying purposes, I left out the error bars, and as you can see, this nutation is very well predicted by our Lagrangian model. Now, as you saw also in the previous slide, even the angular velocity had a slight notation. It wasn't perfectly a straight line. Now, how can we explain this? This can be explained with a notation. If we look at these hurricane balls from a side view and from a top view, then we can first of all say that there's a certain inclination angle as already introduced before. And then we have a normal force, as I already mentioned. This normal force causes a precessional motion, as described when I explained the first observation. And because we have this dissipative rolling friction force, this would produce a torque, which would cause these hurricane balls to start slowly decrease their inclination angle. If we do this, then this normal force decreases because it's accelerating downwards. So if this happens, then this precessional frequency decreases because the normal force's torque is what causes the precession. Now, if this happens, then you can have a look at the top view where you see that this friction force decreases as proportional to the normal force. Now, also then the torque produced by it decreases, and therefore, again, this whole system can stabilize itself. And then we just have the same procedure. It fluctuates again. That's why we have fluctuation in the decrease in angle and also in the precessional frequency. So in conclusion, we can say that we've described the liftoff and the onset. We've explained with different videos. We've shown that airbag is not necessarily important. We've quantitatively explained the steady state motion, and we've also found a novelty, namely a generalized quantitative model for very general hurricane balls, as in the task statement. Finally, we've described the time development with a qualitative explanation for why this happens, and we've given a novelty by introducing a quantitative model. We've explained and predicted the notation, and in conclusion, I would say that we've fulfilled this task statement. Here are my references. Thank you for listening.
Questions from the opponent, please. Okay. So, first of all, did you do any investigations on the starting phase? Because you talked about the starting phase, but I didn't see any plot of course, the angle over time, for example, for the acceleration phase.
For the starting phase, I found different explanations for how we can achieve the starting phase.
Did you do any investigations?
And I was able to control this terminal angular velocity with the pressure applied on these hurricanes.
Okay, and did you do any investigations or modeling of the start using the airstream? So did you model your airstream during the acceleration phase?
I do not have a quantitative model for that, but I have different quantitative explanations, and we can go into that in the discussion.
But you do think that this is important because it's stated in the task?
Not necessarily.
Not necessarily, okay, I disagree with this point. What is the maximum angle possible for the different radii case, and is it different from the...
Yes, it is.
Okay, can you just say it's bigger or it's smaller?
In what case?
In the case where the smaller ball is on the ground.
If the smaller, where you can see...
Just simply state smaller or bigger for the smaller ball being on the ground.
If the smaller ball is on top the large ball.
On the ground.
Well, on the surface. Say that the inclination angle is bigger. Then it can be
this point. You said that... can you actually predict which ball lifts up in both cases? The same radii case and the different radii case?
When there are different radii, then I spun the hurricane balls in such a way that but I can't predict which exactly looks where.
You can't predict? And for the same radii case, can you predict?
No, because it's too
okay. Did you measure any sliding friction coefficient, any rolling friction coefficient?
Yes, I did.
Okay. Was there any frequency time dependency measured during the deceleration? Spinning frequency over time.
Spinning frequency over time. You saw in one of my sketches, in one of the diagrams that I predicted.
Okay. Well, fine. We'll discuss it later. And yeah, maybe you talked about the rate of decay of the angle over time during the deceleration phase. Yes. Is it different for different radii?
Can I brief answer?
Yes or no?
I would say yes.
Okay, thank you very much. Time's over.
Thank you.
And now you have time for preparation of the opposition. ready?
Yeah, I'm ready.
Okay, let's go. The opposition.
Hey ladies and gentlemen, my name is Briem, I'm from a team in Germany, and today I'm going to be the opponent on problem number 6, the Hurricane balls. So first of all, in general, to be reported. I think he did a really nice job presenting the problem of the Hurricane balls, thereby doing theoretical modeling, which also came from very well-known literature. And yeah, he did this really well, giving steady-state solutions only, which we will come to that later. He also did this, or explained the phenomenon quite well, just using simple and understandable sketches so that we can really grasp the phenomenon why the effect of the hurricane balls actually turns out to be, as it is shown. He also used appropriate media, showing us videos and the phenomenon rollout. But however, there was a little bit lack in the qualitative explanation, because in the clarifying question he said that he can't predict which ball actually lifts up, because I think he indeed can predict this, but he just got this point right. And there's an unclear prediction of the stability in the perfectly vertical case, because the theory coming from literature, as I know it, also assumes that the perfect vertical case isn't stable at all, and I think this has to be modified if you just modify for the different radial case. Last but not least, I think, and this was the main missing point in the report at all, there was no prediction of the spinning frequency or the angle over time involvement, which I think is really important. Also for the acceleration phase and the deceleration phase especially. So there was somewhat a missing investigation on the acceleration phase, which I asked for, and he just stated unclear, which he stated unclear. And the airspin, for example, or the spinning freak over time, or the oscillation during the starting phase wasn't covered in the report at all, which I found, not so good. There was also an incomplete investigation of deceleration, so there wasn't a really clear statement on the angular velocity decay actually. To the experiments, he really did accurate and reproducible experiments. However, it was unclear for me using a cup as a ground, because a cup might be curved and therefore the no-slip condition might actually not hold. We discuss on that later. And nearly all important parameters were measured, and even the theory was the theory and experiments was just a little bit added for the different radial case and the distance radial case. Then, however, he connected the two steel balls, where for me it's not really clear how it was actually done. In the theory, for example, he would have also to include the moment of inertia, the added moment of inertia, and the mass of the distance fixation actually. And I didn't really come clear about what mass actually comes added from the distance fixation. And there was indeed, sorry this is wrong, there was indeed a measurement of the rolling friction coefficient. However, I was not clear how it was done, so we'll discuss it later. There was also a missing investigation on the acceleration rates, as I also mentioned in the report slide, and the no-slip position wasn't experimentally verified, as this would be especially to be done for the case we're using a cup where the curvature actually of the ground comes into place. And there was a missing investigation on some crucial parameters, for example the air velocity, because the task especially mentions using an airstream and the initial angles. So somewhat he didn't discuss the initial conditions, therefore also saying that he can't predict which ball actually lifts up, which I think he indeed can. Then to the theory in general, he did a relevant modeling of the most relevant steady state, which is actually known as the hurricane balls, so one ball actually being lifted up. But however, there was no modeling of the acceleration phase, also no modeling of the airstream, as he said in my clarifying question. So only steady state solutions were done, which are already known in literature. So there was no transient solution of the Lagrangian, which could have been easily made, or no modeling of the airstream. It was a little bit unclear how the modification of the theory was done, especially whether he included the moment of inertia or the mass of the distance fixation between the two balls, because in the theory I think he just assumes that the distance fixation doesn't share any mass, or there is no mass added to this. And there was an insufficient model of his deceleration phase. So overall, we think that the task was not thoroughly fulfilled, because he didn't discuss the blowing of the airstream, which is especially mentioned in the task, and he didn't do a thorough investigation of overall the salt phenomenon. Okay, so I would like now to invite you to the discussion, and we'll discuss.
Okay, so please let's start the discussion between the opponent and the reporter, please.
Yep. We'll discuss the 3 points actually in this order, therefore just get any question of phenomena. First of all, I would like to discuss with you the acceleration phase of the hurricane ball. And maybe we can do this qualitatively. I think you showed us one plot where the pressure was plotted over the spinning frequency somewhat. It was a linear dependency. Maybe you can just, is there a jog? Yeah. Maybe you can just qualitatively sketch how the spinning frequency then develops over time actually.
The spinning frequency. So you mentioned this plot where we increase the pressure, and and I showed that we have this terminal angular velocity for this. So
I totally agree to this point, and it was very nice done. But I just now want to see, is it the same for the time involvement? So does the dependency of the pressure actually dominate the phenomenon, or are there other phenomena? Because angular velocity over time might add some.
Well, as I have not investigated, I can't say.
What do you expect? Just positively linear dependency or maximum value or
So
convergence?
to keep increasing the airflow, so you asked me how would this develop over time? Is that your question?
Constant airflow, just the angular velocity over time.
And we would have the same pressure throughout with this air pipe. And so we have constantly the same velocity, which is at these hurricane balls. So this would accelerate these hurricane balls. And I would say that it would somewhat decrease in such a way because the velocities come more and more closer to each other.
Okay, I totally agree to this because just looking at the relative spinning frequency, because as you increase the spinning frequency of your hurricane balls by the airstream, the relative frequency, the relative speed between the air velocity and the hurricane balls actually goes down, and therefore the curve actually has to converge to some values.
Yes.
Okay, so yeah, we have come to this. You didn't mention at all the initial state, and you said you can't predict which ball actually lifts up. Do you have any plots where you actually can show the angle theta over the time for the acceleration phase?
For the acceleration phase, I have not done any experiments on how this increase develops over time.
Okay, but we know this from your steady state solutions. So from your steady state solution, you somewhat say that this is constant.
Oh, no, that's not the case because over time the angular velocity increases, and if the angular velocity increases, the model predicts that also that.
Okay, totally agree to this point, but I just forgot to mention that friction in this case doesn't play any role. So we just assume steady state case, and therefore the angle theta actually has to be constant. But for the acceleration phase, is the angle theta actually increasing with a converge, with a limiting trend, or is there somewhat also other effects going on?
If we are increasing, I mean, we have to first of all clarify which angle theta we're talking about, and so
the same you mentioned in your maybe you can get up the slide where you define your angle theta.
So we have this angle. This angle is the theta.
Yeah, totally fine.
Okay, so as we keep increasing this airflow, you would agree that this angle decreases, correct?
Yeah, okay.
This is because the way this is defined, because if we apply this external force, then this torque which is produced causes the lift.
Okay, I totally agree, but what I'm aiming at is if you start the process by spinning by hand, there actually might arise some oscillation of the angle at the beginning.
The problem is that I have sort of read it, but the problem is how we exactly accelerate these balls. It just says spin them by hand. And there are different ways to accelerate these hurricane balls.
But in the task it is mentioned that you have to spin them by hand. So exactly. I want to just stay by the task and want you just to get qualitatively what actually is the phenomenon when spinning them by hand.
Yes, but there's a different way. There are different ways to spin this by hand. We can also just spin, push them down. If we push them down, then we can also achieve the spin motion. So it is not restricted to just spin them in this kind of way. And as we can see here, there's a clear notation in the beginning. So this angle might fluctuate, as you can see in this video clearly.
This angle might fluctuate and also oscillates as I sketched in, because you sketched in nothing and I sketched in oscillation. In your video, I can see oscillation.
Yes.
Can you start it just from the beginning again? Because I've seen that you roll it and then it just goes like this.
Yes.
And finally reaches steady state.
Yes.
So there has to be somewhat a damping of the system, so the oscillation has also to be damped. Somewhat this. But there also has to be an oscillation.
Yes.
Because at the beginning you have centrifugal force, you have the precession force, and at the beginning phase they just can't either compensate enough. So the maximum angle for steady state might be even higher in this accelerating phase.
Yes, that's totally the case, because we also have in this beginning we have a larger spin in this direction. So this angular momentum points closer to this direction, so it can reach a higher angle. That would be the case when these two angular velocities are equal, because the angular momentum vector points into this direction, so it can't reach such a high angle as would be in this kind of case. That's why we see in this video clearly that at some point it is high.
I get your point, but I don't really get your point why there are different angular velocities, because there's just one angular velocity because of your nose difference. But maybe we move on to the next point. To the next point, maybe to the airstream. You have some modeling for the airstream, I think for the deceleration. Maybe you can go to the slide where you showed us your modeling, especially for the Stokes friction. And then I want to ask you the famous question about the Reynolds number.
Yes, I have calculated the Reynolds number. You see, we assume laminar flow, and we have calculated the.
Maybe just go to the slide that I can see your calculation.
Okay, here you can see my calculations.
I meant the one where you have the Stokes formula. So 6 pi eta.
Yeah, you know the formula, so. But
it was on slide.
It was here.
It was on slide 34.
Yeah, here you see the Stokes friction.
No, slide 34.
We are on slide 34.
So maybe I got this wrong. So basically, you model during the deceleration phase the airstream in laminar case.
Exactly.
What is your Reynolds number?
My radius number, as I can show you on this other slide, I've calculated for our case. And if we calculate this radius number for our case, then you can see that we're in this regime of 4,100.
Okay. Just let me interrupt you. So you say that your Reynolds number is about 4,000.
Yes.
What is the critical Reynolds number to be for the airstream to be modeled in laminar case?
Well, as you can see here on this sketch, in this Moody diagram, we can see that there's a certain transition in the mode of magnitude of thousands, and as this angular velocity decreases over time, we can say that we're clearly in this green area which I've sketched in the system.
So you are assuming a decreasing angular velocity over time, and because you have a minimum angular velocity, even being, for example, 0, because just hurricane points just stand still, you can model this in a laminar case. But I think for the most relevant case where the angular velocity is actually quite high, when the hurricane bolts are spinning in steady state, you might have to model the air friction just with a turbulent case, so with a quadratic dependency in the velocity.
If we have high enough angular frequencies, because as you can see in this sketch here, we start off with an angular frequency of about maximally 100 radians per second. So I think this assumption we take for this model is thoroughly valid.
What is actually the width of the? What does the width of the curve?
Of which one?
The left one.
As I showed in the next slide, we can see that there's just large fluctuations, these mutations which occur in this.
Okay. So the oscillation that has too close to each other.
Yes.
Okay, and
that's why I zoomed in on this right sketch.
Okay, but I can't see any dependency in the air friction because I can't see any damping. So I see an oscillation, and whether I don't really agree that there is an oscillation in the end or a relevant oscillation in the end, but I can't see any damping of your curves because the oscillation, the amplitude just stays.
No, but I mean, as I already mentioned before, I showed you the explanation with the notation, and if this, because of this rolling friction which is experienced here, we have this torque which causes the hurricane bolts to tilt down. Do you agree?
Yeah.
Okay, so if this happens, then this normal force here decreases, and so does its torque. Yeah. So therefore, with a fluctuation.
Okay, I agree with this point, but yes. in your diagram theta over t, I would expect that theta over t would also be damped by the air drag, and the air drag has to be modeled in a quadratic dependency of v, and I even don't see any damping in your curve. So whether you model it in a laminar or turbulent case, I can't see any damping, and I don't get your measurement actually right here. Maybe just to get to the last point, to the de-acceleration phase. How would you expect the rate of decay of the hurricane bolts being dependent on the different radii case, for example? So do you expect that the angle over time goes down just linearly, or with the same? So angle over time in the deceleration phase being just linear, or what? Or does it depend on the radius actually?
If we have different radii in this hurricane bolt, so if one is larger and one is smaller, is that your question? And how does the angle decrease over time if we have such a case?
Is it just faster decreasing with having smaller ball in the ground?
Yes, because I would say the moment of inertia in such a case is smaller, and therefore the angular momentum vector is smaller, and therefore the effect of the torque on this angular momentum is larger, so it will decrease.
Okay, but looking at your diagrams, I can only see an oscillation. The oscillation is independent of any of your moment of inertia, as I can see here, and therefore I can't really see the point, because you stated that the rate of decay has to be different for different radii case and for different radius, and it just really goes faster down if you vary the actually geometry of your hurricane bolts. But I can't see the influence of the geometry in your bolts.
This, as I stated,
because
have you for the special case. This is for the special case where the radii and the mass are equal, but we could of course adjust for the other case.
Yeah, but I also see a linear trend of the omega over time, so I don't really get this, because if you have here a linear dependency, you can't have here linear dependency, so I disagree on this.
But if the experimental data shows that and the model predicts that accurately, I don't see why this should be a weak point of this theory.
Okay.
Yeah, thank you very much for the discussion, and 1 minute summary by the opponent.
Okay, so maybe to summarize my opposition. So first of all, I exactly understand what I've shown you in my opposition presentation. First of all, we covered the acceleration phase, where I asked the reporter to just present me with his own quantitative opinion of the spinning frequency over time dependence, where he mentioned just the right that the spinning frequency has to converge to somewhat an optimum, because the velocity of the hurricane bolts actually might increase, and therefore the relative velocity to the airstream might be just lower. He didn't really came clear about, or didn't sketch in the angled over time dependency correctly, or yeah, didn't even sketch it in. And I mentioned that there has to be some oscillation in the beginning, and he even had a video where he showed the dependency and the oscillation in the beginning, and he didn't come clear about this, so I don't think he really understood what's going on in the beginning and during the acceleration. Then we talked a little bit over the steady state, and there we talked about the angle just being constant and only differed a little bit in terms of the spinning frequency. And last but not least, we talked about the deceleration phase and the airstream modeling, where I just covered it. He can't actually predict or model the airstream in a laminar case, because he also has mentioned his Reynolds number to be clearly in a turbulent regime, having a Reynolds number of about 4,000. Okay.
Okay, thank you very much. Let's have a applause for both the reporting and the and questions by the reviewer.
Okay, thank you, reporter and opponent, for an interesting discussion. So I have a few questions I'd like to ask. Reporter, could you go back slide 35?
25. Okay.
35.
35.
So I noticed that in this graph there's an under prediction of the precession rate, the decay. Yes, it will see the experimental line seems to follow a different gradient. Do you believe that this will lead to turbulent drag?
I disagree.
Okay, so opponent, do you agree that it's due to turbulent drag?
The decrease is due to air drag?
The deviation between theory.
No, it's clearly not between air drag, and I don't really come sure about what actually he is doing here with the linear decrease.
I see, thank you. So could you go to slide 13, please, reporter?
13.
You have measured the tilt angle, but you have also mentioned there is mutation. So this tilt angle, is it an average?
13.
Yes, you have measured the tilt angle, is this an average?
Yes, pardon?
You mentioned there's mutation, so the tilt angle is not constant.
Yes.
So would this be an average of the...
This is taken for a very small period of time. There I measured an angular velocity.
So this instantaneous tilt angle?
Pardon?
This instantaneous tilt angle without considering a mutation?
Yes.
Okay,
this is a steady state motion for a very small period
of time. So could you go to slide 9, please?
9? Okay.
So I believe here you assume that there's the torque by the normal force is equal to gravity. So this assumes that the center of mass is stationary. Am I right to say that it assumes the center of mass is stationary?
Yes.
Opponent, do you agree that it is?
Because of full better of geometry and the no slip condition to behold, the center of mass actually has to be stationary. But I think in this experiment, especially with the cup, therefore having a banded curvature, actually has to experimentally verify that there is no kinetic energy in the Gaussian, and therefore the center of energy.
Thank you. So in reporter, have you verified the no slipping condition?
Yes, I can show you a slide with the verification if you want to. Is that your wish?
Yes.
Okay, so as you can see, I made an experiment where I tracked the velocities and I saw a deviation of 1
Thank you. So may I clarify that in your quantitative investigation into the liftoff, did you assume that the air jet is the main force behind the liftoff?
No.
Then could you explain what's the main mechanism behind liftoff?
I would say there are different mechanisms of how we can achieve this liftoff. One was just by spinning, pushing down on them, and one was just by rotation. So I would say that there are pressure differences in one case where this produces a larger
so it's due to the initial perturbation by the hand.
In one case, and in the other it's because of the surface.
Okay, I see. Opponent, do you agree?
The reason of the liftoff is actually the spinning by hand or having an initial perturbation, but the actually reaching the steady state would be really dependent on the airstream acceleration, I think.
But this can also be achieved without air acceleration, that's why I disagree.
Yeah, I see, thank you. So do you model the motion, do you observe any motion at center of mass?
Of the center of mass?
Yes.
That's the reason why we use the cup, because there we can ensure that because the airstream is flowing in this direction of this cup, that there is not a big deviation that there's not much translation motion of the center of mass.
Okay, I see, thank you.
Okay, thank you, Ash, for your questions, and now we have time for preparation. You can keep the mic for the face. preparation is over, please start your review.
Good afternoon, ladies and gentlemen. I'm Jyrkinen from Singapore, and today I'll be reviewing problem number 6, hurricane balls. So here are the strengths and weaknesses of the report. First, the reporter has quantitatively accounted for various experimental observations. For example, there's a maximum tilt angle, minimum, which is quantitatively accounted for. In addition, its generalized quantitative theory considers various cases, such as distance between ball and unequal ball size, and I feel this is very commendable as it allows for extensively verified its theory. Next, as I mentioned, there's a large experimental range varying multiple parameters such as distance between balls and the ball sizes, ball masses, ball radii. And I feel that this is also very commendable. Lastly, experimentally verified no slipping condition, and I feel that this is a very central assumption in its theoretical model. However, there are also many areas of improvement of this report. First, there's a lack of investigation in transit regime, and its Ilifov analysis because external perturbation, which I disagree with, as I feel that if there's initial spin, it could cause an imbalance in normal forces that will cause liftoff anyway. In addition, and I feel that liftoff is extremely important, as when one ball is out of contact with the floor, this will cause there to be no kinetic friction acting on it. This can result in extremely high frequency, as mentioned in the problem statement. In addition, there's a lack of investigation into the air jet, and the problem statement directs us to blow on them through a tube. And I feel the air jet is extremely important, as this air jet might cause other interesting effects, such as a Magnus effect, and might increase the tilt angle beyond the point which it predicts. Next, there's this steady state which assumes that normal force is equal to gravity, which I believe is not true, as he has clearly investigated nutation, which is quite a high amplitude, as can be seen from his data. And this shows that it's not, the center of mass is not stationary vertically. It also uses Stokes drag which is for turbulent flow, as the Reynolds number is 4,120, which is far above the cutoff threshold of 2,000 for turbulent flow. And as mentioned earlier, it uses center of mass stationary, and there's also a poor experimental theoretical agreement, which I've accounted for using the turbulent, which might be accounted for using turbulent flow. So for the opponent, he pointed out lack of investigation in transient regime and the lack of investigation effects of the air jet, which I feel are very important, as I mentioned earlier. However, there's some trivial points, such as the rolling friction characterization, which I feel is already done, and some missed points, such as the moving center of mass due to nutation, and due to the fact that contact point is spiraling inwards, as the reporter has mentioned in his presentation. So now I'll move on to discussion analysis. So first, they discuss about transient regime, and the balls initially lift up, the opponent raised point there were oscillations, and the reporter believes that angular frequency will reach the upper limit very quickly. So I agree with the opponent in this case, as nutation is due to an initial perturbation from a steady state with constant tilt angle, and I believe that initially, as it's spun by hand, the perturbation will be very large, and thus oscillations would be very large, and this would be interesting and could be investigated further. So next, they discuss about drag forces, and the opponent believes that drag should increase. The opponent believes that the reporter did not sufficiently model the drag, as the reporter used Stokes drag, which is correct for low Reynolds number. However, the reporter has calculated the Reynolds number, and it's around 4,000, which I believe it is turbulent, as the cutoff point for turbulent flow is around 2,000, and this is far above that threshold. And I would suggest that the reporter could model this as quadratic drag. So next, there was a discussion about the dependence of moment inertia on the equations, and at this point, I'll agree with the opponent, as the equations do not show any clear dependence on moment inertia, and I feel that when the distance between the balls becomes much larger, this could change the moment inertia independently of the mass and radii of the balls. This will cause the decay rate, or the decay rate to change. However, the report's theoretical model did not account for this, when it's quite clearly shown in experiments. So in summary, the reporter has given a quantitative discussion on a phenomenon varying multiple parameters such as the ball size and the ball radius, as well as varying distances between balls. However, he missed out some important parts of the question. For example, initial liftoff was not modeled quantitatively. He also did not model the blowing on the balls by an air jet, and I feel this is very important, as mentioned in the problem statement. And the opponent rightly pointed out the limited scopes of the report, including the points I mentioned earlier, and he disagreed with the reporter on the effects of drag and moment inertia. In this case, I'll agree with the opponent in this case, as I mentioned earlier. However, he did not have a conclusive discussion with the reporter, and they still disagree on multiple points. Thank you.
Thank you very much. And now let's give them a chance to connect the projector. And once it's connected, we will start the concluding remarks of the reporter. So please, please.
Okay, thank you. There was, by the opponent was mentioned that the cut curvature couldn't be neglected, but as we can see in this measurement here, are the green areas where the hurricane balls move, and there we can see that clearly this cut curvature, which can be seen in the lower diagram, clearly shows no curvature. The second point I would mention is that they said that I didn't vary the moment of inertia for these different spheres, but as can be seen seen here in this slide quite clearly, I did vary these moments of inertia because, of course, if we vary this distance, the moment of inertia changes. So does it because of the different radii of the sphere. So that's why I use the parallel axis theorem to, in fact, change these moments of inertia. So I think this is not a valid point raised by the point and the reviewer. Another point which was mentioned was that I modeled this time decrease, that I just looked at the steady state motion, if I'm not mistaken. That can be clearly seen here. We see that there are dampening forces which dissipated forces in the system which cause this inclination angle and the angular velocity to change and to decrease over time, or to increase in the case of the angle, because the definition of the angle we took here. So I think this is not a valid point, brought up. Then they also said that I used the Stokes friction, as can be seen here, and as we can see in this graph here, we can clearly see that for the maximum velocities we have for our case, we're clearly in this case of the laminar flow. And as this decreases over time, the angular velocity, we would even move more into this laminar flow regime, and therefore I think the assumption that we take the laminar flow is thoroughly valid, and we can also see that there are no larger deviations between the theory, data and the theory. Also, it was mentioned that there are no oscillations for the velocity, but as can be seen here, there's a thick line, and there is in fact oscillations for this angular velocity. It's not just one line, and this is because of the reasons I showed you before. Then it was also mentioned that I said that this angular velocity reaches the upper limit, but this is not the case, as we can keep increasing at exponential.
Thank you. Thank you very much. We need one more mic for the jury. Yes, we have it. So 5 minutes questions from the jury members, please. John.
Question for the opponent.
Yeah.
You suggest it was indeed possible to predict which ball loses contact with the surface first. Could you very quickly elaborate on that?
Yeah, it is indeed very easy because because of the task as mentioned, you have to spin them by hand, and by spinning by hand, you have somewhat one hurricane ball being initially a little bit more lifted up, and therefore the oscillation at the beginning will start from the initially lifted up ball, therefore giving just an initial torque by lifting up exactly this one hurricane ball. So by just spinning by hand and lifting up one initially, you can actually.
Okay, thank you,
force.
Andre.
Show me slide 37, please.
37. Yes.
The black points are experimental result here.
Pardon?
And
The blue points.
The blue points.
And the brown line is theoretical.
That's the blue line. Yeah.
And you think there is a good comparison of experimental results with your theoretical prediction here?
The measurement isn't very accurate. That's why we have quite large error bars. But I think the general overall
Maybe
trend
I will elaborate on this a little bit. Maybe I just like see something what's not there, but I kind of like see an oscillation pattern here, like if you would use say Fourier transform, I guess you would see a frequency which is say by the order of magnitude difference. So do you have the feeling that?
What do you compare here?
What's the question?
Okay, so my question is that you claim that the blue points have the same frequency as the red line. In my feeling on looking on the points is they have a frequency which is roughly by the order of magnitude higher than the red lines. So my question is, did you anyhow try to compare the frequency of the blue points, say by Fourier transforming them to the frequency of the red points?
I did not do any Fourier transform to confirm this anyway, but I would say the sampling frequency is too low because of the high-speed cameras we use, which only are limited to 500 frames per second.
Okay, thank you. Next question. Peter?
Fast question, page 35.
35.
Presentations that appear on page 35, do they have to prepare any special initial conditions for that, or did they always appear spontaneously, and if yes, why?
It always appears spontaneously, and as I already mentioned, that we have the frictional force at the contact, the rolling friction force at the contact, which causes this torque, which causes finally this rotation.
Thank you. Next question, Maciek?
Did you take into account the mass of the junction of the
Mass of the connection of the two phases?
You mean for the distance, where we have distance. I did not take this into account, but the thing is, we can these masses are relative to the spheres are that small that we don't. It would just make the equations much more complicated, and we couldn't really see this comparison that is actually original formula. So that's why I omitted this. But of course, it could be just easily mathematically done by introducing new moments of inertia of these.
Very brief comment on that one.
I don't think that he has done it because I didn't see it in the equation, and therefore I pointed this one out. And I think it has a really high interest because it lowers or higher, dependent on the mass and moment of inertia, the center of gravity, and therefore also the maximum angle achieved.
Okay, thank you. Andre?
Why do you think the flow isn't laminar?
So it's the reporter has calculated the Reynolds number, and his 4,000, which I feel is quite large. The Stokes flow assumes very slow laminar flow, but the change in momentum of the air around this can be quite neglected.
Okay, brief follow-up on that. So the Reynolds number of 4,000 something, is it for the deceleration or for the blowing phase?
For the deceleration phase.
And what about the blowing phase?
Well, for the blowing phase, we certainly have much higher Reynolds numbers, but that's not why I investigated quantitatively. This is just for the time development after the steady state motion.
Okay.
Yeah, because I thought that he has assumed the Reynolds number and calculated Reynolds number for a pipe flow and even for water, and he should have done this not for pipe flow, and he should have done this not even for water but for air, and therefore it should be much lower, but I don't think that it's really an another case.
Okay, further questions? Conrad?
Question for the reviewer, please. Do you think the reporter ignored the curvature of the cup? Is that appropriate here?
The curvature of the cup. So I feel initially when he spins it, it's not that important as it's verified. The area in which he spins it is very small. When he's blowing it, I believe that this edge might cause the balls to translate slightly, and this might cause it to move to the edges where the curvature is more significant.
I'm sorry. The time's up. Thank you much. We are ready to show the grades for the report. Now, 8, 7, 8, 6, 7, 8, 6, and a 6. Grades for the opponent. Now, 8, 7, 6, 8, 7, 8, 9, 9, 7, 7. And grades for the reviewer now. 7, 8, 7, 8, 7, 9, 7, 10, 8, 8. Thank you very much. So, rather smooth distribution for the report, 3 times a 6, 2 times a 7, and 5 times an 8. So let's say a very brief comment from Maciek. Would you like to comment your 6 for the report?
For me, the experiment part was not done because in full solution it's not fully solved because it was not very well considered. And secondly, in theoretical part, this mass of these magnets in between poles were not taken into account. So it's like
Okay. Yeah, thank you very much. And maybe the partial grades for the 6?
3.5 and 2.
Okay, thank you very much. So I was on the higher side. So obviously one of the reasons was because I was on the higher side for the previous report as well. My partial grades were 4.5, 1.5, 2.5, and minus 0.5 because I don't really agree with your statement on the theory there, and I can somehow subscribe Maciek's criticism, and also somehow you completely neglected the phase of blowing, which was a kind of internal part of the task that by blowing in the air, so you cannot just ignore that part. Anyway, for the opposition, we had a very clear single 6 by Maria.
I thought you had a lot of interesting clarifying questions, but then you didn't touch upon them in the discussion. And then I was not very satisfied with the discussion because I felt you spent the majority of the time trying to get the reporter to draw the wrong graph so that you could point out that he was wrong. So you had good topics, but I felt you didn't really use those to bring forth more understanding on the problem.
Partial grades?
I gave a 0.75 for questions asked, 2.25 for opposition, and 1.75 for discussion.
Thank you. And we had a 9 by Ilya.
Okay, I think that given the fact that in the report there was a lot of results and a lot of things to argue about, you were quite good with your job as opponent because you noticed a lot of different things to discuss. You were very attentive, and at the end you gave your critical opinion about each of your observations in a very clear manner. So I was adding you points for the questions, for your final statement, and also for the discussion. I felt that what you were presenting was quite clear, and my final grade was 9.
Okay, thank you very much, and maybe we can, sorry? Yeah, a little comment.
In your opposition speech, you had very interesting question about the existence of a limit of angle theta, but you didn't discuss it at all.
Okay, thank you, and let's start with the 10 from the Peter, because that's obviously very high grade.
Yes, I think there are 2 reasons for my high grade. One was that I thought maybe more than the other jurors that the reporter and the opponent did a very good job, so I thought it was difficult to add something to it. And I think you added at least 1 point, this shifting of the center of mass. And the other reason is when I evaluate the video, I always think of things that I could have done better myself, I could have added myself. And since I would probably not be a very good reviewer myself, I couldn't think of anything, so I had to give it a 10. Yeah.
And partial grades?
The partial grades were 2 for the questions asked, 2.5 for the review of the reports, 2.5 for the review of the positions, and 2 for the discussion analysis.
Okay, thank you. And Kent, your 7?
Okay, 7. I felt the timing was a little bit off, like more at the start and less at the end. And felt a little bit rushed in the discussion analysis. So I gave 1.5 for the questions asked, 2 for the review of the reports, and then I felt it started to sort of get a bit quick. 1.5 for the review of the opposition, and 1 for discussion analysis.
Okay, thank you. Maybe just a short comment from myself, like at least like my personal feeling was that really the review of the opposition was pretty short and pretty incomplete. So I came to the 7 with a kind of different grading than Kant. I gave you just 0.75 for the review of the opposition and higher points for the other things because it at least for me it looked really like you somehow skipped the opponent and there was place to think about to speak about and also time to speak about. Anyway, I think we have explained our grades by now, and we shall have some like real breaks so that every one of you can go to the toilet and whatever.